Hi everyone, I am Shubham Garg and welcome back to this lecture series of DSCH Software. So in today's lecture, we are going to see how to make NAND and OR gate using CMOS. Okay, so as we all know, NAND and OR gates are the elementary gates, universal gates, and that is what we are going to see how to make them using the CMOS. Alright, so here is the structure of NAND gate, and I will first show the working, that how is NAND gate working, and then we will design the schematic using DSCH software. Alright, so here I will run the simulation, and you can see NAND is not AND, that is, it will work as a complement of AND. So in AND gate, whenever we have 0 0 as the input, we have 0 and 0, that is, we get 0 as the output. But here in NAND, it is not AND, that is the complement of AND gate. So similarly, when we get 1 0 in AND gate, in 1 0, 1 and 0 is 0. However, in NAND gate, it is the complement, that is 1. Similarly, if I on the other input, you can see 1 and 0, again it is giving 1, and in AND gate on 1 1 we get 1 as output, but here since it is a complement, we on 1 1 we get 0 as the output. Okay, so this is how the NAND gate works, and now we will see how we are going to how the circuit is actually working. Okay, so whenever we run the simulation, first you see here both the inputs are 0. Alright, so when the inputs are 0, this PMOS and this PMOS is on, since these two PMOS are connected in parallel. Okay, so both the PMOSs are on, and thus this logic 1, it gets flow towards the output because it is connected to VDD. Similarly, when let's say B input is on and A is off. Okay, so now since both the PMOSs are connected in parallel, the logic 1 still flows from here. Okay, that is from this VDD to the output, and thus we are getting 1 as output. Here you can see the logic 0, that is a ground, it starts flowing from this transistor. However, the other transistor, that is from A, is open circuited because the A input is 0. Okay, and NMOS is not short circuited on 0. So that's why we get logic 1 here. Similarly, when we off B, when we give 0 input at the B and we give 1 input at A. Okay, so now what happens is that due to this 0 input at B, this transistor, this second transistor gets on, and thus logic 1 again flows from this VDD to the second transistor, since it is short circuited, towards the drain, and we get 1 as an output. Here we can see by logic 0 at B, this transistor, the NMOS, becomes open circuited. However, when we supply 1 to A, this NMOS, it becomes short circuited, but there is no logic 0 because the below transistor is open circuited, and this logic 0 can't flow towards the output. And when both of these are 1, what happens is both the PMOS are off, that is open circuited because PMOS is on with the 0 input. So when we give 1 as the input, both NMOS becomes on, that is short circuited, and thus this logic 0 flows towards the output. Okay, so this is and that's why we get 0 as the output. So this is how NAND gate works. Okay, so now we will see how to make this NAND gate. Okay, so I will first of all I will delete this NAND gate, and we will build one from scratch. So now, okay, let us drag PMOS and NMOS to our schematic. Okay, that is the NMOS. We need 2 NMOS and we need 2 PMOS. Okay, because NAND gate has 2 inputs, A and B. So this is PMOS, this is NMOS. So we just need to drag and drop. Okay, so here I am also going to explain how these things are working. So I have just opened Paint. And yeah, so here we will see how why the schematic is made this way. Okay, so first of all, there are few rules, as we have already seen in previous videos, that our schematic using CMOS logic consists of two networks, that is pull up network and pull down network. So we already know pull up network, as the name suggests, it basically gives logic 1 to the output, that is the network consisting of PMOSes, and pull down network that gives logic 0 to the output, that consists of NMOS. Okay, so every circuit, as we have seen in the case of inverter, has the pull up network and the complementary pull down network. Okay, so there are basically some rules for drawing the schematic. Yeah. Okay, one thing is any schematic which we are making using the CMOS logic will be complementary. Okay, any schematic will be complementary using CMOS logic. Okay, and now what that statement means, let me just increase the size first. Yeah, so you can see here any schematic will be complementary. Now what that means is whenever you make a circuit, it will be a complement, it will be in a complemented form. That is, for example, we are making NAND gate here, that is A dot B whole complement, that is complement of AND, that is what we are getting as the output. Okay, we can show complement using either this apostrophe, or we can show using this bar as well. Just a second, I will draw the bar. Yeah. Okay, A dot B whole complement, we can show it like this as well. So whenever we draw a circuit using CMOS logic, we get this complemented circuit as an output. Okay, that, and let's say we need to make an AND gate using this NAND gate, then what we do is we add an inverter at the output, so that it becomes A dot B complements and whole complement after adding the inverter, and that becomes A dot B. Okay, we will see the AND gate in other video. All right, so next thing, this is the first rule, that is whatever we are getting output will be the complementary. Okay, rule number 2 is that whenever there is a dot between them, whenever we have a dot, okay, that is this, you can see A dot B. Okay, then the PMOS, that is pull up network, will be in parallel, and NMOS, that is pull down network, will be in series. Okay, so here you can see, since there is A dot B, so we need two transistors, one for A and one for B. Okay, so both PMOS and the A and B PMOS, since they are having a dot in between, so they will be in parallel, and the NMOS will be in series. Okay, now the third rule is just the opposite of this, that whenever, that is OR sign, okay, plus, that is OR. Okay, let me just increase the size. Yeah, now it seems fine. Okay, here whenever there is OR, okay, PMOS will be in series and NMOS will be in parallel. Okay, so for example, we will see here in the case of NOR gate, after this NAND gate we will be making NOR gate, and we will see it will be like this, A plus B complement. So here the PMOS will be in series and NMOS will be in parallel. Alright, so these are the rules to design any schematic. So using these rules we are going to design our NAND gate and NOR gate. Okay, so now coming back to the circuit, here is our 2 PMOS and 2 NMOS. Also you need to remember that if there is A dot B complement, that is, this is our function A dot B complement. Okay, then the number of transistors which we will be using to design the circuit will be 4 here, because we need a pull-up network for A and B, that is, one transistor for A and one transistor for B in the pull-up network, and similarly we need 2 transistors in pull-down network, that is, one transistor for A and one transistor for B. So one transistor for A let me just reduce the size of it. Yeah, one transistor for A and one for B in pull-up network, and again one transistor for A and one transistor for B in pull-down network. So therefore total transistors is equal to 4. Alright, however, when we design AND gate, the function in the AND gate is A dot B, that is, there is no complement. So here the number of transistors requires is 6. And why is that? Because first of all we require one transistor for A and one for B in pull-up network, and similarly 2 transistors in pull-down network. So these are equal to 4 transistors, plus we are going to we have to add an inverter as well, because the function what we get in output is in the complement form. So to make it into the normal form we need to add an inverter, and if you remember from the previous video, inverter consists of 2 transistors. So we add one inverter at the output, which is equal to 2 transistors. Okay, so therefore we have total 6 transistors. Therefore 6 transistors in A dot B. Alright, we will see that schematic also in the AND gate video. So now now here we are going to focus on the NAND gate and NOR gate. Okay, so let us just make the schematic. So these are the 2 transistors, that is A and B. Okay, and these need to be in parallel because we have a dot between them. Alright, so we will just place it here, and from the wire we are going to make the connections. Okay, let me just show source and drain also for better understanding. So you see here source and drain. So from drain we take the output, and source on the source we supply the logics. Okay, so here we need to get this supply and drag and drop it here. And similarly below we need to get this ground to supply logic 0. Okay, and from here we are going to get the output. Okay, and if you remember, for the output we use this light. Now we need to give input to A and B. Alright, so now you need to remember that one PMOS is connected to one NMOS, another PMOS is connected to other NMOS, and then they are given the input A and B. So first of all we are going to connect this PMOS to, let's say, this NMOS. Okay, and this NMOS should be connected to the other PMOS. So I will just connect here. Yes, so now it is connected. So we have connected one PMOS with NMOS, another PMOS with other NMOS. Okay, you can connect any PMOS with any NMOS, that any order doesn't matter. Okay, now just drag and drop the input. So here is the input 1 and here is the input 2. Okay, so now we need to give the inputs. So one input for the one PMOS NMOS combination, other input to other PMOS NMOS. And now our circuit for NAND gate is ready. So let us just simulate the circuit. So we will run the simulation and we can see when both the inputs are 0, the output is 1. And when we see one input is 1 or any other input is 1, the output still remains 1. But when both the inputs are 1, the output comes to 0. So this is how a NAND gate works. And similarly, we are going to see the functioning of NOR gate. Okay, so I hope this NAND gate is clear, and the NOR gate works in the similar fashion, just there is some changes in the circuit. Alright, so we will see the changes because PMOS will be in series and NMOS will be in parallel in the case of NOR gate. And then after making the schematic, we will see how the NOR gate is functioning. Okay, so I am not going to delete everything here. I will just delete the wires and will make changes to this circuit only. So I will delete every wire here. Yeah, so these wires are deleted, and now let's rearrange PMOS and NMOS. So now we know that PMOS should be in series. So from here, just connect it to series with the supply. So here both PMOS are in series now, and the NMOS should be in parallel. Okay, so here is first NMOS, here is second NMOS. And now both the NMOS are in parallel. So let's just make the connection, okay, and see if it is working properly or not. So here this is connected to source and drain. Okay, you see due to some reason there is not a connection here. So I will just make the connection like this so that it doesn't have any issues in future. Similarly here also I am going to make some connections. Yeah. Okay, so now all our connections are there and it should work fine. So just connect this PMOS to one NMOS, okay, and other PMOS to other NMOS. Okay, just make some connections here because we need to make sure that these are properly connected. Yes, okay, and similarly this PMOS to other NMOS. All right, so we have almost all the connections. Okay, and now what we need to do, we need to connect the inputs. Okay, so this input I have already connected. Now this is the other input and we will connect it here. Okay, there is some line here. I will just delete this wire. Right. Yeah. So now we need to connect the drain, the output to the LED. Okay, and it should work fine. Let's see. Yes. So we can see our OR gate is working. Okay, so let us look at the truth table for, sorry, NOR gate is working. So let us look at the truth table for OR gate and NOR gate, okay, for the better understanding. So I will just delete everything here. Yeah. So now we will see the working of OR gate and NOR gate. So we know that OR gate consists of two inputs, that is A, B, and the output in OR gate is A or B. Okay, just a second. Yeah, so we have A, we have B. Okay, I don't know why it is happening. Let's try once more. Yeah, A, B, and we have A plus B, that is our OR. Okay, so for OR we have the input 0, 0, 1, 1, and similarly for B 0, 1, 0 and 1. Alright, so when we do A or B, what we get is 0, 0 we get as 0, 0, 1 we get as 1, 1, 0 we get again as 1, and for 1, 1 we again get 1. Alright, however, what the circuit which we have made here is the complement of A and B, that is NOR gate, that is A NOR B. Alright, so here when we complement A or B, we get 1 as the output here and 0 everywhere else. Alright, that is when the inputs are 0, we get 1 as the output, and when the inputs are not 0, then we get 0 as the output in the NOR gate. Okay, so this is the truth table, and we can see here in our simulation, when we run the simulation, when both the inputs are 0, we get 1 as the output. When any input is 1 or both the inputs are 1, we get 0 as the output. So now we will see why it is behaving that way. Alright, so if you are following my lectures till now, you most probably have figured it out, the logic why 0 is coming to the output and 1 is coming to the output. But if you are not following, I will recommend you to watch other videos. Okay, and now I will also explain this thing, that why we are getting 1 or 0 as the output. So when we are running the simulation, what is happening, both the inputs are 0. Alright, so when this input is 0, that means the PMOS will be on, okay, that is connected here, and when this input is 0, that will mean that this PMOS, since it is connected to this input, will be on. So both the PMOSs are on, so thus both the PMOS are short circuited, and the logic 1, that is the voltage supply, this flows from here source towards the drain, and we get 1 as the output, because we can see the NMOS, both the NMOSs are open circuited since we supply 0 towards the input gate. Now when I supply 1 to any input, what happens, due to the 1, this PMOS turns off because this input is connected to this PMOS, and we get the open circuit, and we see that this VDD cannot flow towards the output, okay, because this is open circuited. However, this NMOS is short circuited when we supply 1. So what happens, these both NMOSs are connected in parallel, thus this logic 0, that is ground, flows from here, and we get 0 as the output. Similarly, when the other input is 1 and previous input is 0, this PMOS is open circuited, and thus logic 1 flows from here but didn't go past this point. Okay, thus we didn't get logic 1 as the output. However, here in the case, since these NMOSes are parallel, okay, so no matter if this NMOS is open, the other NMOS is short circuited, and thus logic 0 flows from the source to this drain, and we get 0 as the output. Okay, so when both of them are 1, what happens? Both the PMOS are open circuited, and thus logic 0 can't flow. Logic 1 can't flow. And however, the NMOSes are short circuited, and thus logic 0 easily flows towards the output. And this is how NOR gate functions. Okay, so this was the functioning of NOR and NAND gates. Now I hope it will be clear that why when we supply 0 or when we supply 1, we are getting 1 or 0 or anything at the output. So that is how our basic logic gates functions. In other videos, we will see how to make an AND gate or OR gate using this structure. Alright, and what we are going to do is we are going to add the inverter in front of it, so that NOR becomes the complement and it gives the OR gate. So these are our universal gates, that is NAND NOR and NOT gate. Okay, so this we have completed. In the other videos, we are going to see other logic gates, that is XOR and XNOR, and after that we are going to move towards the combinational circuits. So this is all for this video. Thank you everyone.